And then when we get back, we're going to jump into the last part of Unit 7. But I want to make sure we can get through this first. So, it said find the volume. It said find the volume of the figure. There are actually two different figures here. What are the two figures?
Cylinder and cone.
Cylinder and cone. So, your cylinder, the volume is 1/3 area of the base times the distance between the bases.
That's the cone.
That's the cone I meant. I'm sorry. I pointed at the cone and said something else. And then the volume of the cylinder is area of the base times the distance between the bases. So we need to kind of take it one piece at a time. So if you look at just the cone, right? So we have a 16 feet, which represents the diameter, which means that 8 feet is the radius. Why do we need to know that the radius is 8 feet, Tara? Because we use the radius to find the area of the base. So what it really breaks down to is 1/3 times 3.14, which is the pi, and then it's the radius squared, right? Which is 8 to the second power times 6. And then we can pick up our calculators. 401.92. Fantastic. So we end up with 401.92. Any questions on that? On the cylinder, we end up with the same thing. Remember, the area of the base is pi r squared. So we end up with 3.14 times 8 squared times 4. Now, by the way, remember, something that kind of bit some of you on that quiz, make sure you're verifying that every unit of measure is consistent. Because it's really easy for me to make it all in inches and then add like 1 foot as the height or something. And a lot of you are still falling for that every single time. Okay? So then it comes this into our calculator and we get what? 803.84, which is the volume of the cylinder, so we add them up.
1,205.76.
1,200.
Right in here, say 8.8.
1,205.8 cubic feet. Christopher. Wait, I'm sorry, what? I know. Remember when I talked to y'all about the fact that one of the most obvious tricks to give you is to give you the diameter versus the radius, right? So we have to be very, very careful about that. The other trick.
Yeah, because the arrow's pointing up the other side.
Yeah, this is a full line. It's a line showing us.
It's a full red line that's showing.
Dot.
Okay. Just make sure we're mindful of that. Make sure we're being very, very careful about that. Any questions on this? Okay, so to tell you what we're going to do, and then we'll kind of break and go to lunch and come back. Yes. Unit 7 is divided into 2 pieces. The 3-dimensional volume side, which we're basically done with, which is volume of cylinders and pyramids and cones and spheres and half spheres and all that fun stuff. And then transformations. Transformations are when you're on a coordinate grid and you have to know reflections, translations, rotations, and dilations. That's what we're learning. If you look at the schedule this week, so today we're doing translations and reflections. Tuesday we're doing rotations and dilations. Wednesday we're doing compound transformations, which is where we take one and we do multiple things to it that moves around a coordinate grid. Thursday, your review is due. I will give you the reviews tomorrow, but I'll give you 2 days to get it done. And then Friday we're having a unit test. And that's Unit 7 done and out of the way. Okay? Do what?
This is Unit 7.
Yeah.
So
So it involves volume, and it involves what we're doing the next couple of days. Okay, so it's all volume and transformations. Okay? Any questions, by the way? I'm sure some of you listened and some of you didn't. Any questions on the dress code thing? Because they get very, 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 very specific. So today we're going to jump into transformations. We're going to do a couple that, the ones that theoretically you should already know. but I don't really, not absolutely positive based off of what you learned in 5th grade, whether you actually learned what you're supposed to learn or not. You definitely will not need a calculator for this. It's purely how things move around a coordinate grid. Okay? So there are four basic transformations that we have to understand. What do you think a transformation is? Everyone needs to away your phones, by the way. Okay. Yes? What's transformation?
The way something changes.
Yeah. To transform means to change. So a transformation is simply the way that a shape moves or changes primarily in a coordinate grid. Primarily on a coordinate grid. Okay? And the four that we're going to learn about are these are the two we're going to learn about today. Translations and reflections. A translation and a reflection. Okay, tomorrow we'll deal with dilations and rotations, which are a little bit more complicated. You may know what a translation is. What is it, Christopher?
It's the translate to the different.
Okay, you may know what a translation is mathematically, know it?
I think I know what it is.
What is it? Try
Where
it.
you like turn an object to like turn a shape.
Close. It's actually, notice how I kind of wrote it in a weird way? It's because a translation is a slide. A translation is a slide. If you think about, and if you think about what a slide does, a slide, if you have, for example, the letter G, and you slide it, it simply moves, but it maintains the way that it sits. It doesn't turn upside down. It doesn't flip. It literally just slides around. It can slide right, it can slide left, it can slide up, it can slide down, it can slide on diagonals, it can slide any number of ways. But it always stays the same. Okay? If you have the letter F, this, if you see that, you know that there was something else involved other than a slide, other than a translation, because it changed orientation. A translation will never change its size or its orientation. Orientation means how it sits. It just changes where it is. Okay? And then, Cameron, you said a reflection is a reflection is a flip. A reflection is indeed a flip. A reflection is a flip over something called a line of symmetry. A line of symmetry, which is a term you need to understand. The very definition of a line of symmetry is that the object is a mirror image of itself across a line of symmetry. Lamid?
Circle.
Yeah, a circle has lots of lines of symmetry.
Infinite.
Has an infinite number of lines of symmetry. Okay? A rectangle would have how many lines of symmetry?
Either 2, 3, 4, 4. No, 2. It can have 4. 2.
It has two.
If it's a square.
It has two. I didn't say. I drew. It has two lines of symmetry. It has a line of symmetry here, and it has a line of symmetry across the middle. It does not have a diagonal line of symmetry because if you draw a diagonal line of symmetry and try to fold it over on itself, it doesn't match itself perfectly. Okay? So letter B. That is a reflection, theoretically, if I could draw better, of the letter B, because it does mirror itself across a line of symmetry. Okay? So a translation is a slide, and the rules are it cannot change its size and it cannot change its orientation. And a reflection is a flip across a line of symmetry. A reflection is a flip across a line of symmetry. Any questions on that? Okay. So when we look at a coordinate grid, guys, like this, typically what we will do is we will give you a particular shape. So for example, say we have a triangle that's located at A, at B, and at C. So we have this triangle located at the vertices A, B, and C. If I translate it, then it should look exactly like this. It should look exactly like this. It will just be located somewhere else. It will be located somewhere else on my coordinate grid. It will be just located somewhere else on my coordinate grid. It could be here. It could be here. It could be over here. But the one thing that I know is that it will always be facing the same. It will always be facing the same. It will never turn. Tara?
Even if it moves like half down, like there, would that
Still be a translation. Still be a translation. Now, to talk to you about how 8th graders deal with translations, we already know, let me move my triangle back. If I were to graph the ordered pairs for this particular shape, if I wanted to graph, that's not a little hole. If I wanted to graph the ordered pairs for this particular shape, what would the ordered pairs be for the ordered pair be for point A? Brendan?
412.
It would be 412.
No.
And
312 is 3.
it is 312.
Oh, yeah. 312.
Got it. No, it's okay. Let me fix that. Now that is because when we write an ordered pair, we first write the x and we first write the y. Right?
This X is before Y.
Because x is before y alphabetically, but more importantly is because this is the x-axis and this is the y-axis. That's a very important thing to understand about translations. Because if I'm going to slide something, I will typically do it with an algebraic rule. If I were to move this object to the left, would I change the x or would I change the y?
X.
I would change the x. Because the x-axis is my left-right mover. And if I were to move it up and down, I would change my y.
Y.
So the way that you'll see a translation written is they will say translate triangle, and they would actually call this triangle ACB. You might know why?
Maybe because it's
What, Tara? No. What on it? Because when you're naming a shape based off vertices, you always go clockwise. So I would have to go A, C, then B. And by the way, you will find tons of times where your teacher does it incorrectly. And you may tell your teacher, whoever that is, because it will not be me, that Mr. Smith said you're doing it wrong. Because it should always be titled vertices in a clockwise way. Okay? It doesn't matter where you start, but it doesn't matter which direction you go. So you could call that triangle CBA
or BAC.
or BAC. Yes,
Okay. Why couldn't we do A, B, C?
because that's not clockwise.
See
See what I'm saying? It has to go in a clockwise motion. It has to go clockwise. I mean, clock, this is the way the clock rolls. Okay, so it always has to go in that direction. Huh? Oh, Tessa, yeah. Dude, that's one of those things that mathematically people get wrong all the time. Drives me crazy. It's driving me nuts.
If you get it wrong, I'm gonna point you out though.
Do it. I should be. I guess that's being wrong. I'm better being wrong than something. Okay. So now here's the way that they'll tell you to translate. They'll say translate triangle ACB using the following rule. Now the easiest way to move something is one vertex at a time. I would strongly recommend that you move it one vertex at a time. But what you might want to do in your head is write down what direction and how many am I moving it based off the rule that you see. Jason, x minus 2 means we're going to move it which direction and how many?
To the left, 2 units.
To the left, 2 units. Perfect. And if we do y plus 1, we're moving it
Up.
up 1. So it's left 2, up 1. And then once you get that in your head, then it's just a matter of taking the vertex and going left 2, up 1, left 2, up 1, and left 2, up 1. Now we have to label those vertices. You might know the rule on labeling the vertex. Claire? What's the rule on labeling the vertex? Were you just stretching? You might know how you label a vertex once it's been moved. Christopher? Sure, but what do we label it? Because we already have an A.
A2.
No. Alex?
A.
No.
C, E, F, G.
Element O key. A prime is how you know that a point has been moved once. And this would become C prime, and this would become B prime. And then you know that your vertices have been moved.
What's the volume?
There's no such thing as a volume of a two-dimensional figure.
Oh, because there's two triangles.
Yeah, you can do area. You can absolutely do area. But we know that the areas must be what? The same. Because it didn't change size. Now, a couple of other things you need to know. Our original is called the pre-image. Our original figure is called the pre-image. And our transformed shape is called the image.
Why would it be called a post-image?
I know, it's not. It's just called the image because it's like the reflection. It's what's happened after the move. And they do test that a lot on the 8th grade test. They'll give you like the image and they'll give you the translation and say find the pre-image. If they give you the image and the translation, what must you do to find the pre-image, Nolan?
I'll work backwards.
You must work backwards because it's already been moved.
These two fingers upwards.
Yeah. Well, yeah, exactly. You're just basically going backwards. Okay? So just make sure you're aware of what image and pre-image are, that you're aware of how a translation works, and then you're in good shape. Remember, your test for a translation is always down. Let's put that away because it's dropped off. Very much decided. Okay? It must always be oriented the same. Any questions on that at all? Good to go? All right. So let's talk about reflections. Now, reflections are typically reflected across one of two lines of symmetry. Anybody have a guess as to which two lines of symmetry they like to use? Leilani? They use the horizontal and the vertical axes, also known as what? The y-axis and the x-axis. They will tell you to reflect across or on the axis. They mean the same thing. Sometimes they'll say reflect across the y-axis. Sometimes they'll say reflect on the y-axis. They mean the same thing. Reflect across and reflect on. Now let's talk about what happens based off how you end up doing it. So let's do it now. Let's do a rectangle. Here, and here, and we'll label them.
A, B, C, and D.
Wait.
B, A, C, K. Element of B. B, A, C, K. Element of D.
Okay. We're going to label this one after me. Okay, we're in rectangle. H-U-N-K.
Hunk.
No.
You ever heard the term hunk?
No.
It means
Oh, not referring to. I know what it means.
it means I am beautiful. We're going to reflect.
Should have been a P.
Should. Wow! Oh,
Hunk.
nicely played, sir. That was well done, Alex. You just, I'm good. You said no compliment, but you got it. Okay, so let's do this first. H-U-N-K. I want write down the ordered pairs for H-U, N, and K, please. Write down the coordinates, the ordered pairs for H, U, N, and K. That was funny.
I did not look.
I'm still gonna hit you with something, but that was funny.
It did not mean what you think.
Oh, I know what it meant.
No.
I'm gonna have you reflect rectangle FAIL.
Fail.
Look at you. Like 30 minutes later, we'll be like, oh, that's funny. Okay, so right on the coordinate grid, so I want to make sure that you can write coordinates because that's going to be an important part of this. You should have gotten for H is 2, 6. For U is 8, 6. For N is 8, 2. And 2, 2. Now, if they said reflect across the y-axis, reflect across the y-axis, what you need to understand is that a reflection is a what? What was the remember word?
Minus some flip.
Flip. A reflection is a flip. So it's not that it's just going across the y-axis, it's actually flipping over the y-axis. Another way to think about it is that each vertex must be equidistant, bless you, from the line of symmetry. So the K is 2 away from our y-axis. Therefore, this would represent K prime. And that would make this H prime. U would be 8 here and here. So this makes this U prime, and this makes this N prime.
Wouldn't it be switched because it has to clockwise, so it wouldn't be
No,
H Q and K, it would be H, K, and U?
it would not. It would not because it's now an image. It's a reflection. But what you have to understand is that this correlates to this correlates to this, and to this. Now, what I'd like you to do really quickly is I want you to go ahead and find what the coordinates are for our new points. What are the ordered pairs for the new points?
No.
That's exactly what you do.
That's what I said.
So when you reflect across the y-axis, what's actually happening to the ordered pairs?
Making all the other big things.
Making all the x's their opposites. So -2, 6, -8, 6, -8, 2, and -2, 2. So when you reflect across the y-axis, the x's go to their opposite. They don't go negative because they might have started as negative, right? They just go to their opposites, which means when we reflect across the x, we're going to do what?
Flip the Y.
Flip the y's.
Yep.
Flip the y's to their additive inverse. And that's how you reflect. That's how you reflect. Making sure that you label them properly. Which means that a lot of times, like even on our translation, did we really need to have the image in order to apply that translation rule? Do you know where I know A prime is? What's the ordered pair for A prime?
113.
113. Now, how many of you went 113, and how many of you simply plugged in the x here and the y here? That's a better way to do it. You don't always have to have a coordinate grid to apply a rule, if you understand the rules. Sarah? Uh-huh. That's very good. Now watch this. So what if it's not something that's so nice? What if our triangle was located here, here, and here? So triangle
XYZ.
Here.
XYZ.
US.
R-A-T.
Exactly. That's what I was gonna say.
And I said, I would like to reflect this across the x-axis. I want to reflect this across the x-axis. Where would the A land? Where would the A land, Bennett? Give me the order pair. 2. There. Is it equidistant from your line of symmetry? Is it equidistant from your x-axis?
It's 2, 2.
Correct. Because we were at 2, -2, remember when we flip across the x, we just change the value of the y. So we know that it should end up at 2, 2. That is A prime, which is located at 2, 2. It's flipped over the x-axis, which puts R, which is at -2, 4, where would it go?
2, 2.
What's the only value that's changed when you flip across the x? The y. So it goes to -2, -4. That is R prime. And t, which is at -2, -2, goes right there. So our triangle is now reflected or flipped. It is reflected or flipped across the x. Right? Yes. Now, here's the thing. Do not apply the trick if you don't remember the trick. Because at the end of the day, you could just say, okay, so if I'm going to flip the A across the X, then whatever this distance is, I need this distance to be. You can just flip it, no problem. Now, if you can remember, okay, I flip across the X, I change the Y. If I flip across the Y, I change the value of the X. Then by all means do that. I will tell you that our things tomorrow, the rotations, get a little complicated. A rotation becomes a little bit complicated. There are actually rules you have to memorize. Any questions on this? Okay, so translations and reflections. Tomorrow we do dilations and rotations. Here's your task today. You have a classwork sheet and a homework sheet. Listen carefully. The classwork sheet is one page front and back. The homework sheet is one page front and back. They're basically identical. It will take you no time to do them both. You will complete the classwork. You will check your answers against the answer key. You may then throw them away and pick up your homework. You may not pick up your homework until the classwork is completed and checked against the keys. Any questions on that?